micropipette, starting with a regular disposable pipette and a Bunsen burner. Turn on the gas, and the idea is to set up the Bunsen burner so that there's a nice blue cone, a real hot spot. What we're going to do is heat the glass, and then we're going to, once it's melted, draw it out into a nice, long, thin fiber. So hold the glass sort of in the blue hot cone in the middle of the Bunsen burner. Move it from side to side to get it nice and warm. And this frankly takes a lot of practice, and probably the case that I'm going to screw this up. But if everything works out great, you should be able to pull a fiber out pretty much as long as you can stretch your arms. So what I did was I took that original 6-inch pipette and I turned it into a fiber. It turns out to be a hollow fiber still, about 6 feet long. And then what I'm going to do is cut this up, and what I have is a whole series of little micro pipettes that I can spot using these to spot my substrate onto my stationary phase in thin layer chromatography. Chromatography is the general name for a procedure that allows you to separate a mixture. And there's a common element in all types of chromatography. Let me give you some examples of the types first. There's gas chromatography, in which you use chromatography to separate a mixture of gases. There's high-performance liquid chromatography, or sometimes high-pressure liquid chromatography, HPLC, in which you separate liquids. And what I'm going to show you here is thin layer chromatography, or TLC, that allows you to separate, in this case, organic compounds. Now, the name chromatography comes from the fact that originally things were separated by the fact that they look different, and that's exactly what we're going to use here. Today, there are all kinds of really fancy techniques for determining when you've separated two compounds using this chromatographic method. So chroma, meaning color, is somewhat of a misnomer today, but all of these techniques still have in common techniques with what the original chromatography was, and that's what we're going to look at today. So the elements that are common to all chromatography are that you have some sort of stationary phase, and in this case we're going to use a piece of filter paper as our stationary phase, and then you have a mobile phase, something that moves, and in our case we're going to use water, and then the third thing you have is substrate, or your mixture, and our mixture is a little bit of grape Kool-Aid. Now, you might have thought, how come there isn't purple in food coloring? Food coloring typically comes in blue, red, yellow, and green. And the answer is, you don't even need those 4 colors. You actually need 3 colors, because green is actually a mixture of yellow and blue. So you could just use the 3 primary colors in order to get all the different colors of food that you might want to eat. And in particular, grape Kool-Aid is purple. What we're going to see is that purple is not really purple, it's something else. All right, so we have our stationary phase, and the first thing that you want to do when you do thin layer chromatography is you want to mark the baseline where you're going to spot your substrate. So what I've done is I've drawn a line parallel to the bottom of the stationary phase in pencil. It's important to do it in pencil because pencil doesn't elute. Pencil's not going to go anywhere. If you did it in pen, the ink might actually start moving along on your chromatogram, and you'd be chromatographing ink. Now I have this micro pipette that I made earlier out of a regular pipette by heating it in a flame and then stretching it out. And what I'm going to do is spot the substrate down onto my stationary phase. And the idea is to get a small, tight spot. It's a little challenging because we've got an aqueous solution of grape Kool-Aid here, but I'll do the best that I can. And what I'm going to do is I'm going to put a couple of spots down so that we can compare what's going on. Now, one thing you might do is, after you spot it down on your stationary phase, blow on it a little bit to dry it out before you respot it, and use sort of a stabbing motion to try to get a little tiny spot if you can. Okay, so here I've got my stationary phase, it's got the line drawn, and then I've got my substrate, the grape Kool-Aid. And now I'm going to transfer it to my chamber, and my chamber consists of a beaker that's got a little bit of water. The level of the water has to be below where I spotted my substrate, because we want the water to, by capillary action, move up the stationary phase, but we don't want the purple to go into the water. So, and I've folded this in half because this filter paper is not very stiff. You may or may not have to do that depending on what kinds of stationary phases you use. Another common kind of stationary phase is to use something like silica gel on a glass plate, and then of course you wouldn't have to fold it because it would be stiff. Okay, so let's set it up like that. And already you can see, let me get this out of the way, that the original purple spot is separating into two other spots. In particular, it's separating into a blue spot that seems to be moving a little bit faster, closer to where the solvent front is, and then the red spot, which is lagging behind. So there is no purple food coloring. What we're looking at is a mixture of red food coloring and blue food coloring. Okay, one of the spots seems to be running amok. It's running sideways, so that one's not going to work so well. Part of the problem here is that I wanted to put enough material on that you could get a good look at it. We'll ignore the one on the right, which is going sort of curved, but the one on the left looks pretty good. Now, I did this a little bit earlier, so what I'd like to do now is set this aside. We can come back to it later, but set this aside and show you how we calculate RFs, or retention factors, for these compounds. So let's do that. Again, I did this experiment a little bit earlier, and here we have the stationary phase with the two substrates, or the two components of the substrate, pretty well separated. And they streaked really bad, so this is not an ideal case. We would probably spend some time trying to optimize the mobile phase so that we got a dot moving up the paper that was about the same size as the dot we originally spotted, as opposed to something that's really streaky like this. But in any case, we can estimate how far the particular spot moved by just taking the middle of the range of the spot. So let's say that blue moved that far and red moved that far. And then what we do is we measure how far the spot moved relative to the baseline. So, for instance, red moved 38 millimeters. So red moved 38 millimeters. And blue moved 55. And then the solvent moved all the way up to the top of the plate, and that's 67. Okay, so we define RF, and actually I think it's little r, is equal to the distance that one of our component moved over the distance that the solvent moved. Which is equal to, for red, divided by 67, 0.57, and for blue, 0.82. Okay, now you can ask, why do they separate? Why do red and blue separate? And the answer is the molecules that make up the red dye and the blue dye have different polarities. And what we're witnessing is a competition between the affinity of the dye for the stationary phase, which is the piece of paper, and the mobile phase, which is the water. Water is very polar. The stationary phase is, the piece of paper is actually also polar as well. And depending on sort of how well the dye, particular dye, sticks to the paper versus wanting to move along with the water determines the fact that we get different RFs for these two compounds. Okay, well, let's go back to our original chromatogram here, and it's tipped over, but we can straighten it out. And it looks like our channel on the right has actually straightened itself out, and you can see that they're well on their way to being entirely separated. It looks very much like the chromatogram that I ran earlier. And again, this is an example of thin layer chromatography, which is used to separate these two food coloring dyes from purple Kool-Aid, to show you that there's no such thing as purple. Well, maybe not no such thing, but in this case, it isn't that there is food coloring that's colored purple here, but rather a mixture of blue and red.